This is some of the craziest mathematics they didn't even bother to teach us at school. In the world of mathematics, we learn to climb a ladder of operations. We start with addition, the simple step forward. Then we learn about repeated addition, which we call multiplication, a faster way to travel. From there, we take a leap to repeated multiplication or exponentiation, a powerful jump to a whole new scale. But what happens if we keep climbing? What if exponents had exponents? This new idea represents a profound jump in complexity. We can visualize this growth. Addition is like a simple walk in the park. Multiplication lets us cover more ground, like jogging past a growing tree. Exponentiation is a launch into another dimension entirely, a blast-off that leaves the familiar world behind. But the operation beyond that is an explosion of complexity, a fractal universe unfolding from a simple rule. This is tetration, the math operation that breaks reality. It's what you get when you start stacking exponents to infinity. First things first, you know addition. Repeated addition gives us multiplication. Repeated multiplication gives us exponentiation. And at the top of this ladder of arithmetic, repeated exponentiation gives us tetration. This strange new symbol is how we write it. And the most important thing to remember is that you always solve it from the top down. Let's start small. For 2 tetrated to 2, we build a power tower 2 blocks high. This is simply 2 squared, which gives us 4. Easy enough. Now let's try 2 tetrated to 3. We build our tower 3 blocks high. This means 2 to the power of 2 to the power of 2. Remembering our top-down rule, we first solve the top 2 blocks. 2 squared is 4. We're left with 2 to the power of 4, which gives us 16. But what about 2 tetrated to 4? We build the tower 4 blocks high. 2 to the power of 2 to the power of 2 to the power of 2. Again from the top down. 2 squared is 4. 2 to the power of 4 is 16. And finally, 2 to the power of 16 is 65,536. That number might seem random, but it's incredibly important. It's the exact number of colors available in the 16-bit color palette that defined the look of classic video games. But why stop at 2? Okay, let's try base 3. 3 tetrated to 2 is simply 3 cubed, which gives us 27, about the number of squares on a Rubik's Cube. Manageable, but 3 tetrated to 3 is 3 to the power of 27, a number with 13 digits, roughly 7.6 trillion. If a person represented one, this number would be a colossal sphere, dwarfing them completely. 3 tetrated to 4 is 3 to the power of 7.6 trillion, a number so vast that if you started writing it at the Big Bang, 1 digit per second, you wouldn't even be close to finished today. And 4 tetrated to 3, that's 4 to the power of 256, a number with 154 digits. It dwarfs the number of atoms in the observable universe like a galaxy dwarfs a single speck of dust. Tetration isn't just another operation. It's a mathematical chain reaction, an explosion of scale. What happens when we build a power tower that goes on forever? Does this infinite stack of numbers actually mean anything? Does it converge to a finite value? To find out, we can rephrase the problem. If the tower converges to a value, let's call it L, then we can say that L is equal to our base, A, raised to the power of the rest of the tower. But since the tower is infinite, the rest of the tower is also L. This gives us a simple equation, L equals A to the power of L. We can solve this graphically by looking for the intersection of two functions, y equals x and y equals A to the power of x. Let's try a base of the square root of 2. We can see how the value bounces back and forth, spiraling inwards, getting closer and closer to a single point of intersection. For the square root of 2, the infinite tower converges to exactly 2. But this doesn't always work. If we choose a slightly larger base, like 1.5, the intersection points are still there, but our spiral now flies outwards, getting further away with every step, diverging into infinity. So, where is the tipping point? The boundary between convergence and chaos. It lies at a beautiful transcendent number, e to the power of 1 over e, or about 1.44. Below this value, the tower is stable. Above it, it explodes. This razor's edge is the same boundary that defines some of the most intricate and famous fractals in mathematics. Beyond the simple operations lies a deeper kind of math, a kind of real math magic governed by functions like the Ackermann, which grow at rates that are difficult to comprehend. This magic is built upon a ladder of operations. We start with addition. Repeated addition gives us multiplication. Repeated multiplication gives us exponentiation. And repeated exponentiation gives us tetration. But the ladder doesn't stop there. The next rung up is pentation. 2 pentated to 3 is defined as 2, tetrated to the result of 2 tetrated to 2. We know that 2 tetrated to 2 is 4, so 2 pentated to 3 becomes 2 tetrated to 4, which we've already seen is the mind-bendingly large number 65,536. This process of repeating simple rules to create staggering complexity isn't just a mathematical curiosity. It's a fundamental pattern woven into the fabric of reality. We see it in the infinite detail of fractal geometry, in the chaotic yet patterned fluctuations of financial markets, and in the branching diversity of biological evolution. All of these seemingly different worlds are connected by the same deep magic, the power of iteration. We've seen how tetration builds infinite towers, how it spirals into chaos at the edge of convergence, how it climbs a ladder of hyperoperations, and how it launches us to scales beyond comprehension. But this has all been a bit of a trick. You see, mathematics isn't the backstage skeleton of music. It's the neon choreography we've been grooving to all along. Class dismissed. Go spin some numbers. So, what is X? It's tetration plus extra reverb, and that's the end of our journey for now. We've seen how a simple idea, repeating an operation, can lead to numbers that dwarf the cosmos and patterns that echo the deepest structures of our universe. The story of numbers is a story of infinite encores, with each new operation revealing a deeper, more beautiful magic.